RecNMP accelerate personalized recommendation with near memory processing. Abstract. Personalized recommendation systems leverage deep learning models and account for the majority of data center AI cycles. Their performance is dominated by the memory-bound sparse embedding operation with unique and regular memory access patterns that pose up fundamental challenges to accelerate. This paper proposes a right way, commodity and compliant near-memory processing solution to accelerate personalized recommendation inference. The in-depth characterization of the production-grade recommendation model showed the embedding operation with a high model and operator and data level parallelism lead to memory bandwidth saturation, limiting the recommendation inference performance. We propose RecNMP, which provides a scalable solution to improve system throughput, supporting a broad range of sparse embedding models. RecNMP is specifically tailored to a production environment with a heavy co-location of operators on a single server. Several hardware and software co-optimization techniques such as memory-side caching and table-aware packing scheduling, and hard entry profiling are studied, resulting in up to 9.8 times memory latency speedup over a highly optimized baseline. Overall, RecNMP offers a 4.2 times throughput improvement and 45.8% of memory energy savings. Introduction. The personalized recommendation is a fundamental building block of a memory. Many internet services still used by the search engines, the social networks, so online retail, and content streaming. Today's personalized recommendation systems leverage deep learning to maximize accuracy and deliver the best user experience. The underlying deep learning models now consume the majority of the data center cycle spent on AI. For example, recent analysis revealed that top recommendation models collectively contribute to more than 72% of all AI inference cycles across Facebook production data centers. Despite the large computational demand and production impact, relatively little research has been conducted to optimize deep learning DL-based recommendation. Most research efforts within the architecture community have focused on accelerating the compute-intensive, highly regular computational pattern found in a fully connected FC, convolution, CNN, and recurrent RNN neural network. Unlike CNN and RNN, the recommendation models exhibit low compute-intensive and little to no regularity. Existing acceleration techniques either do not apply or offer small improvement at best, as they tend to exploit regularly usable data flow patterns and assume high specialty locality, which are not the main performance bottleneck in recommendation models. Given the volume of the personalized inference and the rapid growth rate occurring in the data center, an analog effort to improve the performance of these models would have a substantial impact. To suggest personalized content to individual users, recommendation models are generally structured to take advantage of both continuous dense and categorical sparse features. The latter are captured by large embedding tables with sparse bucking of the pooling operations. These embedding the operation dominate the runtime of the recommendation models and are markedly distinct from other layer types. A quantitative comparison of low compute and memory access requirement is shown in Figure 1a. Sparse embedding operations, represented by a sparse length-on (SLS), consist of a small sparse lookup into a large embedding tables followed by a reduction of the embedding entries, that is, pooling. They present two unique challenges. First, while the sparse lookup working set is comparatively small in bits, the irregular nature of the table indices exhibit pure predictability, rendering the typical pre-batching and data flow optimization techniques inactive. Second, embedding the tables are on the order of tens of the hundreds of gigabytes, overwhelming the on-chip memory resources. Furthermore, the circular points in Figure 1b show the operation intensity of LSL is orders of magnitude less than FC layers. Low intensity limits the potential of the custom hardware, including the specialized data path on-chip memories used in the CNN RNN accelerators. The result is a fundamental memory bottleneck that cannot be overcome with standard caching, for example, tiling, the algorithmic input batching, or hardware acceleration techniques. This paper proposes RecNMP, a near memory processing solution to accelerate embedding operations for ML-based recommendation. RecNMP is a lightweight DIMM-based system built on the top of existing standard DRAM technology. We focus on DIMM-based near memory processing instead of resorting of the specialized 2.5D and 3D integration processes, for example HBM. The DIMM form factor with commodity DDR4 devices can support the 100 GB more capacity plus more capacity necessary for production scale recommendation models with low cost. By eliminating the off-chip memory bottleneck and exposing the higher external bandwidth, we find that RecNMP provides a significant opportunity to improve the performance and efficiency by lifting the roof line by the 8 times for the bandwidth constraint region, Figure 1b. Therefore, enabling the optimization of TME opportunities not feasible with the existing system. So we have performed a detailed characterization of recommendation models using open source and production scale DLRM benchmark as a case study. This analysis quantified the potential benefits from the near memory processing in accelerating recommendation models and build the intuition for the co-designing the NMP hardware with the algorithmic properties of recommendations. Specifically, it highlights the opportunity for the RecNMP architecture in which bandwidth-intensive embedding the table operations are performed in memory and compute-intensive FC operators are performed on CPU, or potentially on an accelerator. The proposed RecNMP design exploits DIMM and rank-level parallelism in DRAM memory systems. RecNMP performs local lookup and pooling functions near memory, supporting a range of the sparse embedding inference operators, which produce a general gather-reduce execution pattern. In contrast to the general-purpose NMP architecture, we make a judicious design choice to implement a selected lightweight functional unit with a small memory side caches to limit the area overhead and power consumption. We combine this right-way hardware with the software optimization, including table-aware packet scheduling and host entry profiling, compared to the previous work whose performance evaluation is solely based on a randomly generated embedding accesses. Our characterization and experimental methodology is modeled after representative production configuration and is evaluated using a real production embedding table traces. Overall, the RecNMP leads to a significant embedding access latency reduction, 9.8 times, and improved end-to-end recommendation inference performance 4.2 times, as illustrated in Figure 1b. So our makes the following research contributions. Our in-depth workload characterization shows that our production recommendation models are constrained by the memory bandwidth. Our calorie analysis using production embedding table traces revealed distinctive spatial and temporal use patterns and motivate a custom designed NMP approach for recommendation acceleration. We propose RecMMP, a lightweight DDR compatible near memory processing architecture. RecNMP accelerated the execution of a broader class of the recommendation models and exhibited 9.8 times memory latency speedup and 45.9% memory energy savings. Overall, the RecNMP achieved 4.2 times end-to-end throughput improvement. We examined hardware-software co-optimization techniques, memory-side caching and table-aware packet scheduling, and hot entry profiling to enhance the RecNMP performance and customize the NMP instruction with 8 times the DRAM command address bandwidth expansion. A production-aware evaluation framework is developed to take into account common data center practices and representative production configuration, such as model co-location and load balancing. The Chapter 2, Characterizing the Deep Learning Personalized Recommendation Models. This section describes the general architecture of the DL-based recommendation models with prominent sparse embedding features and their performance bottleneck. As a case study, we conducted through thorough characterization of the recently released deep learning recommendation model, DLRM benchmark. The characterization latency breakdown, the loop line analysis, bandwidth analysis, and memory locality illustrate the unique memory requirements and access behavior of the production scale recommendation models and justify the proposed nearly memory accelerator architecture. A. Overview of the personalized recommendation models. Personalized recommendation is a task of recommending content to users based on their preference and previous interaction. For instance, video ranking. For example, Netflix and YouTube. A small number of videos out of potentially millions must be recommended to each other. Thus, delivering a accurate recommendation in a timely and efficient manner is important. Most modern recommendation models have an extremely large feature set to capture a range of user behavior and preferences. These features are typically separated out into dense and sparse features, while dense features, that is, vectors or matrices, are the processed by the typical TNN layers, that is, FC, CNN, RNN. The sparse features are processed by the indexing large embedding tables, so the general model architecture of the DL-based recommendation system is captured in Figure 2. A few examples are listed with their specific model parameters in Figure 2b. A similar mixture of dense and sparse features are broadly observable across many alternative recommendation models. Embedding table lookup and pooling operations provide an abstract representation of sparse features learned during training are central to the DL-based recommendation models. Embedding tables are organized as a set of potentially millions of vectors. Generally, embedding tables operations exhibit gather reduce pattern. The specific element-wise reduction operation varies between models. For example, GAFE that comprises a family of embedding operations prefixed by the sparse length, that is, sparse length weighted sum A-bit the row-wise, that performance similar gather or reduce embedding operation with quantized weighted summation. The SLS operator primitive is widely employed by other production scale recommendation applications, for example, YouTube and Fox. So our work aims at alleviating the performance bottleneck and improve the system throughput by the devising of novel NMP solution to apply the SLS family embedding operation, thus covering a broad class of recommendation systems. B. A case study based on the LRM benchmark. To demonstrate the advantage of a near-memory processing for S-scale personalized recommendation models, we study phases of deep learning recommendation models, DLRM. So the dense features are initially processed by the bottom FC operators, while the sparse input features are processed through the embedding the table lookups. The output of these operators are combined and processed by the top FC, producing a prediction of a click-through rate of the user item pair. This paper focuses on the performance of the acceleration strategy for four recommendation models representing two canonical classes of the models, RM1, RM2. These two model classes attribute to significant machine learning execution cycles at a Facebook production data center. RM1 over 30% and RM2 over 25%. The parameters to configure them are shown in figure 2b, and a notable distinguishing factor occurs each configuration is the number of the embedding tables. RM1 is comparatively the smaller model than U embedding tables, so RM2 has tens of embedding tables. In production environment, recommendation models employ the three levels of parallelism shown in figure 3 to achieve the high throughput under strict latency constraint. Model level parallelism grows by increasing the number of concurrent model inference. So on a single machine, the operator model parallelism adds a parallel thread per model and data level. Parallelism is scaled by the increasing batch size. On SLS, the operator performs a batch of the pooling operations. One pooling operation performs a summation of a set of the vectors. The input to SLS for one batch embedding lookups including inside vector containing sparse IDs and optionally a weighted vector. C. Operator bottleneck study. We observed that the SLS family of operators is the largest contributor to the latency and recommendation models, especially as batch size, data level parallelism increases. Figure 4 depicts the execution time breakdown per operator, with the majority of the time spent executing FC and SLS GAP2 operators. With a batch of the 8, SLS accounts for 37.2% and 50.6% of the model execution time of RM1 small and RM1 large, respectively, whereas for larger models represented by RM2 small and RM2 large, a small significant portion of the execution time goes into SLS, 33.5% and 68.9%. Furthermore, the fraction of time spent on the submitting embedding table operation increases with a higher batch size, 37.2% to 61.1% and 50.6% to 71.3% of RM1 small and RM1 large respectively. Note that the execution time of the RM2 large is 3.6 times higher than RM1 large because RM2 comprises higher number of parallel embedding tables. Generally, the embedding table sizes are expected to increase further for models used in the industry. The loop-line analysis. Applying to the loop-line model, we find recommendation models lie in the memory bandwidth constraint region. close to the theoretical loop-rhyme performance bound. We construct the loop-rhyme describe the theoretical limit to the data system described in section 4. We use the Intel Memory Latency Checker (MLC) to derive the memory bound. We derive the compute bound by sweeping the number of fused multiply add FMA unit to in a processor in the operating frequency of the CPU. Turbo mode enabled. So figure 5 represents loop-line data point for models RM1 and RM2 as well as their corresponding FC and SLS operators separately. We sweep the batch size from 1 to 256 with darker colors indicating a larger batch size. We observe that the SLS operator has a low compute but higher memory requirements. The FC options of the model has a higher compute needs, and the combined models in between. SLS has low and fixed operational intensity across batch sizes as it performs vector lookup and element-wise summation. FC operational intensity increases with batch size as you requested in the batch share in the same FC weights. Increasing FC data reuse with increasing batch size. The FC operator moves from the region under the memory bound loop-line to the compute bound region. For the full models, we find RM1 and RM2 in the memory bound region. As operational intensity is dominated by the high percentage of SLS operations. It also reveals that the increasing batch size, the performance of SLS, as well as the RM1 and RM2 models, is approaching the theoretical performance bound of the system. More importantly, our loop-line analysis suggests that the performance of the recommendation model is within 35.1% of the theoretical performance bound, and there is a little room for further improvement without increasing system memory bandwidth. By performing the embedding, looks up the pooling operation before crossing the pin-limited memory interface, near memory processing can exploit higher internal bandwidth of the memory system, thus effectively lifting up the loop-line and fundamentally improving the memory bandwidth constraint performance bound. E. Memory bound of the production configuration. Executing the embedding operation on real systems can saturate memory bound at high model, operator, and data level parallelism. Figure 6 depicts the memory bandwidth consumptions as we increase the number of the parallel SLS threads for different batch sizes, blue curves. The green horizontal line represents the ideal peak between the 76.8 GB per 4-channel and DDR4 2400, and the red curve is the empirical upper bound measured with the Intel MLC. So we observe that the memory bandwidth can be easily saturated by the embedding operations, especially as batch size and the number of threads increase. In this case, the memory bandwidth saturation point occurs batch size 256 and the thread size is 30, where more than 67.4% the available bandwidth is taken up by the SLS. In practice, a higher level of the bandwidth saturation beyond this point becomes undesirable as memory latency starts to increase significantly. 36. What is needed is a system that can perform the gather reduce operation near memory such that only the final output of the pooling returns only the CPU. F. Embedding table locality analysis. Prior work has assumed that the embedding tables lookups are always random. However, we show for traces from production traffic, There exists a modest level of locality, mostly due to the temporal use. While recommendation models are limited by memory performance generally, we wanted to study the memory performance generally. We wanted to study the memory locality to see if caching can improve performance. We evaluated both random traces and embedding tables and looked up traces from production workload used by the Eisenman et al. In production system, our recommendation model contained tens of embedding tables and multiple models are co-located on a single machine. To mimic the cache behavior of the production system, we simulated the cache hit rate for multiple embedding tables co-located on the machine. Figure 7. Combed 8 means 8 embedding tables learning on the machine and the T1, T8 traces, each for a single embedding tables, are interleaved for 8 embedding tables. For combo 16 and combo 32 and combo 64, we multiply the 8 embedding tables 2, 4, 8 times on the same machine, which also approximates larger modes with 16 and 32 and 64 embedding tables. We use the LRU cache replacement policy and a four-way set associative cache. We assume each embedding table is stored in a contiguous logical address space and randomly mapped to 3 physical pages. To estimate the amount of temporal locality present, we switch the cache capacity between the 8 to 64 MB with a fixed cache line of the 64 byte. In figure 7a, the random trace has a low hit rate of the 5% or less than 5%, representing the worst case locality. We see that the combined simulation of production traces is much higher than a random, with a hit rate between 20% to 60%. More importantly, hit rate increases as cache size increases. In section 3D, we will show how optimization to RecNMP can take advantage of this locality through the table-aware, the packet scheduling, and software locality hints from batch profiling. Spatial locality can be estimated by sweeping the cache line size of 64 to 512 bytes with a fixed cache capacity of 16 MB. Figure 7b illustrated sweep for the combo 8. We observed that as the cache line size increases, in fact, the hit rate decreases. In order to isolate the effect of the increased conflict misses, we run the same experiment on fully associative cache and observe the similar trend of decreasing hit rate. Thus, we conclude that embedding the table lookup operation have a little spatial locality. Chapter 3. RecNMP System Design. Considering the unique memory-bound characteristics and the sparse and irregular access pattern of the personalized recommendation, we propose RecNMP, a practical and right-way near-memory processing solution to accelerate the dominant embedding operations. It's designed to maximize the DRAM length level parallelism by computing directly and locally on data fetched from the concurrently activated links. First, we employ a minimalist style hardware architecture and embedded a specialized logic unit and a length level cache to only support the SLM family inference operators instead of general purpose computation. The modified model is limited to the buffer chip within the DIMM without requiring any change to the community DRAM devices. Next, the sparse, irregular nature of the embedding lookup exerts a high demand on demand address CNA bandwidth. This is addressed by the sending a compressed instruction from over the standard memory interface, conforming to the standard DRAM physical pinouts and timing constraint. Other proposed NMP solutions have employed special NMP instructions without addressing the CA limitation of the irregular and low spatial locality memory access pattern. We also present a hardware-software interface for host NMP coordination by adopting the heterogeneous computing program model similar to OpenCL. Finally, we explored several hardware-software co-optimization techniques, memory-side caching, table-aware scheduling, and hot entry profiling that provide additional performance gains. These approaches leverage our observation from the workload characterization in the previous section. A. Hardware architecture. System overview. RecNMP resides in the buffer chip on the DIMM. The buffer chip bridges the memory channel interface from the host and the standard DRAM device interface, using data and CA pins as illustrated in Figure 8A. Each buffer chip contains RecNMP processing unit PU, made up of the DIMM NMP module and the multiple link NMP modules. This approach is non-intrusive and scalar, as large memory capacity can be provided by populating a single memory channel with multiple RecNMP equipped DIMM. Multiple DDR4 channels can also be utilized with the software coordination. The host-side memory controller communicates with the RecNMP PU by sending customized compressed formal NMP instruction through the conventional memory channel interface. The PU returns the accumulated embedding the pooling result DIMM.sum to the host. Regular DDR4 compatible CA and data signals DDR.CA and the DDR.DQ are encoded by the RecNMP PU from the NMP instructions and then to all DRAM devices across all parallel lengths in a DIMM. By replacing the logic at length level, RecNMP is able to issue concurrent requests to the parallel lengths and utilize. For SLM family operators, the higher internal interface bandwidth is present under the memory channel. Its effective bandwidth thus aggregates across all the parallel activated lengths. For example, in Figure 8A, a memory configuration of 4 DIMMs times 2 lengths per DIMM could achieve 8 times higher internal bandwidth. So, the DIMM NMP module first receives the NMP instruction through DIMM interface and then forwards it to the corresponding link NMP module based on link address. The link NMP decodes and executes the NMP instruction to perform the local computation of embedding vectors. Concurrently, we do not confine a SLS operation to a single length, but support aggregation across the length within the P. This simplifies the memory layout and increases bandwidth. DIMM and NMP perform a remaining element-wise accumulation of the partial sum vectors P-sum and from a partial length to arrive at the final result DIMM sum. In the same fashion, P-sums could be accumulated across multiple RecNMP PUs and with software coordination. We will next dive into design details on the DIMM NMP and link NMP models. While they are on the same buffer chip, having Separate logical modules make it easy to scale to DIMMs with different numbers of lengths. So DIMM-NMP module to dispatch the NMP instruction received from the DIMM interface. DIMM-NMP module employs DDR5 and the protocol engine similar to the design of a conventional DIMM buffer chip. RAM, DRAM, CA, and DQ signals from and to the most toasted side memory controller. The instruction is multiplexed to the corresponding length based on the length ID as shown in figure 8b. DIMM NMP buffers P-sum vectors accumulated by each length NMP in each local registers and perform the final summation using an adder tree before sending the final result back to the host via the standard DIMM interface. Depending on the memory system configuration and the number of the lengths within the DIMM can vary, changing the number of input of the to the adder tree. RecNMP module RecNMP uses the internal bandwidth of the DIMM to increase the effective bandwidth of embedding table operations. Thus, the majority of the logic is replicated for each length. Three crucial functions are performed by the RecNMP module, translating the NMP instruction into low-level DDR/CA commands, managing memory side caching and local computation of the SLS family operators. As illustrated in figure 8, the NMP instruction is encoded to the controls and register inputs. To address the CA bus limitation, all of our DDR commands for a single SLS vector is embedded in one NMP instructions. Three-field is the NMP instruction. DDR and the presence and absence of the active RD PRE with bit 1 or 0. Vector size, V size, and the DRAM address, D address, determine the DDR command sequence and the burst length. These are fed to the local command decoder, like a command decoder, to generate the standard DDR style ACT and RD and FRE command to communicate with the DRAM services. The tags are set at runtime by the address location of a consecutive embedding process. This keeps the CMD decoder in RecNMP right way, as the host side memory controller has performed the heavy lifting task of the requesting reordering, arbitration, and clock and refresh signal generation. If a 128-bit vector with a byte vector with size 2 requires ACT and PRE from a low buffer means the command sequence to DRAM devices for the NMP instruction is PRE, ACT, and low, and RD plus 8 decoded from active and RDPRE and via size tags. Our locality analysis in section 2 shows that the modest temporal locality with some embedding tables as a vector are reused. The operand of each SLS family operates very so caching. The final result in DIMM or CPU will be ineffective. We incorporate memory side cache, length cache, in each length NMP module to exploit the embedding vectors reuse. The length cache in REC NMP takes hints from the locality bit in the NMP instruction to determine whether embedding the vector should be cached or bypassed. The detailed method to generate the locality bit hinted through the Hot entry profiling will be explained in Section 3-D. The entries in the rank cache are tagged by the DRAM address field D address. If the locality be in the NMP, instruction indices indicate how locality and the memory request bypasses the rank cache is forwarded to the rank command decoder to initiate the DRAM read. So the embedding tables are only during the reference, so this optimization does not impact correctness. The data path in RecNMP module supports a large range of SLS family operators. The embedding vectors returned by the rank cache or DRAM devices are loaded to the input embedding vector registers. For weighted sum computation, the weight registers are populated by the weight field from the NMP instruction. So for quantitative operators such as SLS 8-bit operator, the quantized parameter, scalar, and the bias are stored within the embedding vectors and can be fetched from a memory to load to a scalar and bias registers. The weight and the scalar bias registers set to be 1 and 1 or 0 during execution of non-weighted and non-quantized SLS operators. The psum tag decoded from the NMP instruction is used to identify the embedding vectors belonging to the same pooling operations as much pooling in one batch for one embedding table could be served in parallel. The control counter, vector sizes register, and final sum registers in both DIMM-NMP and RecNMP module are all memory mapped, easily accessible, and configurable by the host CPU. B. CA Bennett expansion. Although theoretically the aggregated internal bandwidth of RecNEM scale linearity with the number of length of the processor, in practice, the number of concurrently activated lengths is limited by the CA bandwidth. Due to the frequent row buffer misses conflict from low spatial locality, accessing folder embedding table entries in memory required a large number of ACT and PRE commands. The reason is the probability of accessing two embedded vectors in same row is quite low. As a spatial locality only exists in contiguous DRAM data for burst of one embedding vector. In production, embedding vector size range from 64 byte to 256 byte with low spatial locality, resulting in consecutive low buffer hits the narrow range of 320. To fully understand the CA bandwidth limitation, we analyze the worst-case scenario when the embedding vector size is 64 bytes. A typical timing diagram is presented in figure 9a. It shows an ideal sequence of the bank interleaved DRAM reads that could achieve one consecutive data burst. In this burst mode, the ACT command first sets the row address, then the RD command is sent accompanies the column address. After TRL DRAM cycles, the first set of 2 to 64-bit data, DQ0 and DQ1 appear on the data bus. The burst mode for lasts for 4 DRAM cycles, burst length 8, and transmits a total of 64 bytes on the DQ pins and both rising and falling edge of the clock cycle signals. Modern memory system employed bank interleaving, therefore in the next burst cycle, 4 DRAM cycles. data from the different bank can be accessed in a sequential manner. In this ideal bank interleaving case, every 64 byte data transfer takes 4 DRAM cycles and required 3 DDR commands, ACT, RD, PRE, to be sent over the DIMM CA interface. This consumed 55% of the CA bandwidth. Activating more than 1 week concurrently would require issuing more DDR commands, thus completely exhausting the available CA bandwidth of conventional memory interface. So to overcome CA bandwidth limitation, we propose a customized MMP instruction with a compressed format of a DDR command to be transmitted from memory controller to the RecNMP PUs. Figure 9b illustrates the timing diagram of interleaving NMP instruction to a 4 DIMMs, two lengths per DIMM memory configuration. 8 NMP instructions can be transferred between the memory controller and DIMM interfaces in 4 DRAM data burst cycles on double data rate. In low spatial locality cases, 64 byte embedding vector and 1 NMP instruction per vector, an ideal bank interleaving. We could potentially activate the 8 parallel lengths to perform 8 times 64B lookups concurrently in 4 DRAM data burst cycles. Although the customized instructions have been proposed before 8.23 and 64, our solution is the first one to directly deal with the CA bandwidth limitation using DDR command compression that enables up to 8 times bandwidth expansion for small-sized embedding vectors, that is, 64 byte with low spatial locality. Higher expansion ratio can be achieved with larger vector size. C. Programming model and execution flow. Like previous NMP designs, RecNMP adopts a heterogeneous computing programming models, for example, OpenCL, so where the application is divided into host cores running on CPU and NMP, and kernels being offloaded to the RecNMP PUs. NMP kernels are compiled into packets of NMP instructions transmitted to each memory channel over the DIMM interface to RecNMP PUs. Results of the NMP kernels are then transmitted back to the host CPU, and figure 8D, which is 79-bit NMP instruction, contains a distinctive field that are associated with the different parameters in an embedding operation. A locality hint bit, locality bit, and the polling tag, psum tag, passed between the hardware-software interface. The proposed NMP instruction format can be within the standard 84-bit CA and DQ interface. Using a simple SLS function called in figure 10a as an example, we walk through the execution flow of a proposed RecNMP programming model. First, memory is allocated for SLS input and output data and is marked up as either host cacheable or NMP non-cacheable regions to simplify memory coherence between the host and RecNMP. So variables containing host viable data and such as the two arrays indices and lengths are initialized and loaded by host and are cacheable in the host CPU cache hierarchy. The embedding depth entry EMB in memory is initialized by the host of a host as a host non-cacheable NMP region using the non-temporal hint NTA. So next, the code segment marked as NMP kernel is compiled to package of NMP instruction, figure 10b. A single SL-NMP kernel containing one batch of embedding poolings can be split into multiple NMP packages, with each packet having one or more pooling operations. The NMP instrument belonging to a different embedding pooling in one NMP packet are tagged by psum tag, and the maximum number of the pooling in one packet is determined by the number of bits of the psum tag. We use 4-bit psum tag in our design, At runtime, the NMP kernel is launched by the host of the special hardware driver of support to handle NMP packet offloading and access to the memory management unit NMU and the request memory for NMP operations and the virtual memory system for logical to physical address translated figure 10C and the offloaded NMP package bypass L1, L2 and eventually arrive at the host side memory controller with the NMP extension to avoid scheduling the NMP package out of order based on the FR, FC, FS policy. The NMP extension of the memory controller includes the extra scheduling and arbitrary logic. As illustrated in figure 10D, the memory controller with the NMP extension receives the concurrent NMP package from a parallel execution of multi-host cores, which are stored in a queue. Once scheduled, each NMP packet is decoded into queue NMP instructions. Physical to DRAM address mapping is then performed and the FR, FC, FS scheduler reorders the NMP instructions within a packet only and not between the packets. Instead of sending direct DDR command, ACT, RDPR actions are compressed into 3-bit DDR and filled in the NMP instruction. The host side memory controller also calculates the correct accumulate counter value to a configuration memory mapped controller register remap REC NMP PU. Finally, after the completion of all counter controlled local computation inside the REC NMP PU for one NMP packet, the final summed result is transmitted over the DIMM interface and returned to the output cacheable memory region visible to the CPU. D. Hardware-software co-optimization. Our locality analysis of production recommendation traffic section 2F illustrated intrinsic temporal reuse opportunities in embedding table lookups up, and we propose to memory side caches length side inside the NMP modules to extract more performance from memory side caching. We explore two additional hardware-software co-optimization techniques. This locality-aware optimization results in a 33.7% memory latency improvement and 45.8% memory access energy saving. Detailed performance benefit will be presented in section 5. First, to preserve the intrinsic locality from embedding lookups residing in one table, we propose to prioritize the scheduling NMP packets from a single batch request to the scheduling embedding the table together. Table-aware packet scheduling. In production workloads, the memory controller receiving the NMP packet from the parallel SLR thread with equal scheduling priority. The infra-embedding table temporal locality is not easily retained because of the inference from a lookup operation of multiple embedding tables. This locality can be further degraded when multiple recommendation models are co-located. Therefore, as illustrated in figure 11, we propose an optimized table-aware NMP packet scheduling strategy to exploit the intrinsic temporal locality with a batch of requests by ordering packages from the same embedding table in one patch first, allowing the embedding vectors to be patched together, thereby retaining the temporal locality. SLR operators access separate embedding tables as running in parallel thread in mechanism of implementation comes from the 3-thread level memory scheduler. Next, we propose another optimization technique, hot entry profiling, built on the top of the observation that a small subset of the embedding entries exhibit relatively higher reuse characteristics. We profile the vector of the indices used for embedding table lookup in the NMP kernel and mark the entries with a high locality by explicitly annotating NMP instrumentation with a locality bit. NMP instruction with a locality bit set will be cached in the length cache. Otherwise, the request will bypass the length cache. This hot entry profiling step can be performed before model inference and issuing the SL request and only cost less than 2% of the total end-to-end execution time. We provide the indice of each incoming batch of the embedding lookups and set locality bit if vectors are accessed greater than t times within the batch. Infrequently less than t times, vectors will bypass the length cache and are read directly from the DRAM devices. We sweep the thread T, the pick the value with the highest cache will hit rate to use our simulation. This hot entry profiling optimization reduces cache contention and the eviction caused by the less frequent entries in length cache. Figure 12 depicts a hit rate improvement when the different optimizations are applied. Conv 8 indicates the overall hit rate and model level of the 8 embedding tables Ti1 to T8. To gain more insight, we investigated the hit rate of embedding the tables T1 to T8. In Conv 8, the ideal bar indicates periodical hit rate with infinitely sized cache. With the proposed the optimization, the measured hit rate closely approaches the ideal case across the individual embedding tables, even for traces with limited locality T8. Illustrating the proposed techniques that can effectively retain embedding vectors with a high likelihood of reuse in length cache. Section 4 of Experimental Methodology. Our experimental setup combines real system evaluation with cycle-level memory simulations as presented in Figure 13. For real system evaluation, we run production scale recommendation models on several server-class CPUs found in the data center. This allows us to measure the impact of the accelerating embedding operations as well as the side effect of improved memory performance of the FC operation end-to-end models. Cycle-level memory simulations allows us to evaluate the design trade-off when the DRAM allows augmented with the RecNMP. So Table 1 summarizes the parameters and configuration used in the experiment. We ran an experiment on a 18-core Intel Skylake with a DDR4 memory. To DRAM simulation used standard DDR4 timing from the Micron datasheet. So the real system evaluation, we configure the DRLM benchmark with the same model parameters and traces in Figure 2b in Section 2. The workload characterization Section 2 and the real system experiment Section 4 are performed to a single socket Intel Skylake server specification in Table 1. Cycle-level memory simulation, we build the RecNMP cycle-level simulation framework with four main components. 1. Physical addresses mapping module. 2. Packet generator. 3. Locality-aware optimizer. And 4. Cycle-accurate model of the RecNMP PU consisting of the DRAM devices. Length cache. Arithmetic and control logic. We use a Remerator to conduct cycle-level evaluations of DDR4 devices. On top of the Remerator, we build a cycle-accurate LRU cache simulator for length cache and model of the 4-stage pipeline in length NMP module. CATIC is used to estimate the access latency and error and energy of the length cache. The hardware implementation used to estimate the latency, error area, and the power of the arithmetic logic is built from the Synopsys design compiler with the commercial 4nm technology library. To estimate the DIMM energy, we use CAC-T, 3DD for DRAM devices, and CAC-T I/O for off-chip I/O at the DIMM level. During simulation, we emulate the scheduling packet generation steps taken by the software stack and memory controller. First, we apply the standard page mapping method to generate physical addresses from the trace of the embedding lookups by assuming the OS randomly select 3 physical pages for each logical page frame. This physical address trace is fed to the emulator to estimate baseline memory latency. For RecNMP workloads, the packet generators divided the physical address trace into packets of NMP instructions sent to cycle-accurate model. Next, when evaluating systems with hardware-software co-optimizations, the locally aware optimizer performed the table-aware packet scheduling and hot entry profiling and decided a sequence of NMP instructions. The RecNMP activated all the lengths in the parallel, and traditional DRAM bank interleaving is also used. For each NMP packet, performance is determined by the solo list length that receives the heaviest memory request load. RecNMP and DIMM NMP logic units are pipelined to hide latency of memory read operations. The total latency of the DRAM NMP includes extra DRAM cycles during initialization. To configure the accumulated counter and vector size and register and cycle in the final stage to transfer some to the house. The latency in DRAM cycles of the major components including length cache and the length NMP logic performing the weighted partial sum and final sum are table 1. Section 5. Evaluation results. This section presents a quantitative evaluation of RecNMP and shows it accelerates end-to-end personalized recommendation inference by up to 4.2 times. We first presented the latency improvement of floated SLS operators on a baseline system for analyzing different optimizations, including the placement with page coloring, memory side caching, and table-aware packet scheduling and hot entry profiling. We compare RecNMP with the state-of-the-art NMP systems, Tensor, DIMM, and Chameleon. And we also analyze the effect of the RecNMP on the correlated FS operators. Finally, an end-to-end evaluation throughput improvement and the energy saving at the model level and the area model hover at is presented. A. SLS operator speedup. In theory, because RecNMP exploits length-level parallelism, speedup will scale linearly with the number of lengths and a number of DIMMs in a system. Therefore, we choose for memory channel configuration, number of DIMMs times number of lengths per DIMMs and correspond to 1 times 2, 1 times 4, and 2 times 2, and 4 times 2. The demonstration range of the system implementations. Basic RecNMP is designed without a length cache. We start by evaluating RecNMP without a length cache RecNMP base. In the addition to the varying the DIMM per length configuration, we sweep the number of poolings in NMP packet, where one pooling and the LRM is sum of the 80 embedding vectors. In figure 14a, we find the LSL latency indeed scales linearly as we increase the number of activate blanks in a channel. Latency also decreases when there are more pooling operations in NMP packet. The variation we observed as well as the performance gap observed between the annual speedup and the theoretical speedup 2 times 4 2 lengths and 4 times 4 lengths and the 8 times 4-8 length system is caused by the uneven distribution of embedding lookups across the lengths. As the lengths operate in parallel, the latency of SLS operation is determined the slowest length, the length that runs more embedding lookups. The figure 14b shows the statistical distribution of fraction of the workload on the slowest length. When the NMP packet has fewer NMP instructions and workload distributed more unevenly, resulting in a longer tail with a decreased average speedup. So to address the load imbalance, we experimented with a software method to allocate an entire embedding table to the same link. One software approach to perform such data layout optimization is paging coloring, as indicated as in figure 14a. Page coloring could achieve 1.96 times, 3.83 times, 7.35 times speed up in a 2-rank, 4-rank, and 8-rank system compared with the DRAM baseline. The specific page coloring mechanism can be implemented in operating system by assigning a fixed color to the page frames used by the individual embedding table. The virtual memory system would need to be aware of the DRAM configuration to allocate pages of the same color to physical addresses that map to the same length. This data layout optimization can lead to near idle speedup, but it requires maintaining the high model and task level parallelism, such as multiple NMP packets from different SLS operators can be issued simultaneously to all variables lengths. The RecNMP with the length cache and co-optimization. The memory side caching at the length level with the table-aware packet scheduling and hot entry profiling is one of the key features of RecNMP. These optimizations are described in section 3-D. In figure 15a depicts the performance benefit, that is latency reduction, enabled by applying the different optimization techniques. In adding a length cache, scheduling accesses to the same table together. 3. Adding a cacheability hint bit from software using a configuration 8 lengths and 8 pooling per packet. We observed 14.2% latency improved by adding a 128 kilobyte length cache and additional 15.4% improvement by prioritizing the scheduling of the NMP packets from the same table and batch. And finally, the combined optimization, scheduling plus profile, we pass the cacheability hint after profiling the indices in the batch, which reduces the cache contention, allows the low locality request to not marked for caching of the bypassed cache length cache, so delivering another 7.4% improvement. The total memory latency speedup achieved by offloading SLS to an optimization design RecNMP opt is 9.8 times. In figure 15b, we sweep length cache capacity from 8 kilobyte to 1 megabyte and display how cache size affects the normalized latency and cache hit rate. When length cache is small, for example 8 kilobyte, the low cache hit rate, for example 24.9%, leads to high DRAM access latency. The performance reached the optimal design point at 128 kilobyte. Further increase of the cache size has marginal improvement on hit rate, since it already reached to the compulsory limit in the trace. Yet it incurs longer cache access latency and degrades overall performance. Performance comparison, we compare the RecNMP with state-of-the-art NMP designs such as Chameleon and Tensor DIMM, and both DIMM-based near-based processing solutions. Tensor DIMM scales the embedding operations performance linearly with the number of parallel DIMMs. Since non-NLS operators are accelerated by GPUs in the tensor DIMM, which is orthogonal to a near-memory acceleration techniques, we only compare its memory latency speedup with the RecNMP. Camelon does not directly support embedding operations. We estimated each performance of the Camelon by the simulating the temporal and spatially complex multiplexed CA and the DQ timing of the Camelon NDA accelerators. In Figure 16, as RecNMP exploits length-level parallelism, its performance scales when either the number of DIMMs and length increase, whereas Camelon's tensor DIMM only scale by increase in the number of DIMMs. This is evident as you sweep the memory channel configuration. When the increased number of lengths per DIMM, RecNMP can deliver 3.3 to 6.4 times and 2.4 to 4 times 8 times better performance than the Camelon and tensor DIMM. It is also worth noting that RecNMP has performance advantage 1.9 times and 1.4 times, even in configuration with one-link DIMM, thanks to memory-side caching, table-aware packet scheduling, and hard entry profiling optimization techniques. Neither Chameleon nor Tensor DIM includes the memory-side cache to explicitly take advantage of available locality in memory access patterns, hence their performance with respect to memory latency is agnostic to traces with different amount of the data reuse. In contrast, RecNMP design can extract 40% more performance, shown as shaded from production traces when compared to fully random traces. B. Efficient operator speedup. Although RecNMP is designed to accelerate the execution of SLS operators, it can also improve the efficient performance by elevating the cache contention caused by the model co-location. As the degree of the data level parallelism increases, the efficiency weight brought into the cache hierarchies have higher reuse, normally resulting in a few cache misses. However, when co-located with other models, reusable efficiency data are often vetted early from the cache by SLS data, causing performance degradation. Figure 17 shows the degree of the performance degradation on the co-located efficiency operators. The amount of performance degradation experienced by efficiency layers varies by the efficiency size, the degree of co-location, and the pooling values. When examining the efficiency performance in baseline system, we observed worsening the efficiency performance with larger efficiency weights at the higher co-location degrees and higher pooling values. RecNMP effectively reduced the pressure from the cache contention. We showed base RecNMP design, but RecNMP opt to impact efficiency performance equally as it offloaded the same SLS computation. This beneficial effect, ranging from 12% to 30%, is more pronounced for the large FC, whose weight parameters exceed the capacity of the L2 cache and reside mainly inside the LLC cache. For smaller FCs whose working set fits inside the LLC cache, so the smaller FCs whose working fits inside the L2 cache, for example, all bottom FC and RM1's top FC. The relatively improvement is comparatively lower, up to 4%. C. End-to-end model speedup. Throughput improvement. To estimate the improvement of the end-to-end recommendation inference latency, we calculate total speedup by weight, the speedup of both SLS and non-SLS operators. We measure the model level speedup across the four representative model configurations shown in Figure 18. Not surprisingly, the model that speeded the most time running SLS operators. RM2 largely receives the highest speedup. In Figure 18, the performance improvement obtained by RecNMP varies in batch size. In general, the model level of speedup increases the larger batch size as a proportion of the time spent in accelerated SLS operators grows. Figure 18c looks at the overall effect of the increase in the correlation, the presence of the random of production trace for both CPU baseline and our proposed RecNMP solution. Co-location generally increased the system throughput at the cost of degrading latency. So compared to the random traces, the locality present in the production traces improved performance. However, this locality performance bonus varies of the level of the model. Co-location increases due to the cache interference from the growing number of the embedding tables in multiple models. Applying the RecNMP in the 8-link system result in 2.8 to 3.5 times and 2.2 to 4.0 times end-to-end speed of RM1 large and RM2 small as the number of the co-located models increases. Because the fraction of the SLS latency rises, the improvement of the both latency and throughput enabled by RecNMP is clearly observed compared to the baseline system. Memory energy and savings. Comparison with the baseline DRAM systems, RecNMP provided 45% 8% memory energy saving. RecNMP saved energy from the reduced data improvement between the processor and memory by performing local accumulation near DRAM devices and leakage saving from the reduced latency. So in addition to by incorporating memory side caching and applying co-migration techniques to improve the link cache hit rate. At least RecNMP achieved extra energy saving by reducing the number of DRAM accesses. The area power overhead. We estimated RecNMP design overhead assuming the 250 MHz clock frequency and 40 nanometer CMOS technology. The area and power numbers are derived from the Synopsys design compiler DC for the arithmetic and control logic and CACT for SRAM memory, that is link cache. Table 2 summarizes the overhead of each RecNMP processing unit for both a basic configuration without a cache and optimized configuration with the cache optimizations. Comparing to the Chameleon, which embeds 8 CGRA cores per DIMM, our RecNMP PU consumed a fraction of the area, 4.1%, 6.5% for NSC-NMP base and RecNMP opt, and power 4.6 to 5.9%. When scaling RecNMP PUs to multiple lengths in a DIMM, the total area of power will grow linearly, but is also translated to linear scaled embedding speedup. Given that a single DIMM consumes 13 watts and a typical buffer chip takes up 100 mm square, RecNMP incurs a small area power overhead that it can easily be accumulated without requiring any changes to the DRAM devices. Section 6 is performance characterization of the recommendation models. Recent publications have discussed the importance of scale of the personalized recommendation model in data center. Compared to CNNs, RNNs, and the FCs, the analysis demonstrates how the recommendation models have a unique storage, memory bandwidth, and a compute requirement. For instance, illustrate how Facebook personalized recommendation models are dominated by embedding table operations. To the best of our knowledge, RecNMP is the first to perform locality starting using the production scale models with representative embedding traces. The embedded DRAM-based near memory and near data acceleration. Many prior works explored the near memory processing unit 3D, 2.5D stacked DRAM technology. Due to their limited memory capacity, 16 to 32 GB, and a high cost of ownership, These schemes are not suitable for large-scale deployment of recommendation models 10 seconds to 100 tens to hundreds of gigabytes in production environment. Cameron introduced the approach to practical approach to performing near memory processing by integrating CGRA types of accelerator inside the data buffer devices in accommodate LRDIMM. Unlike Cameron DIMM level acceleration, RecNMP exploits link level parallelism with a higher speed potential. RecNMP also employs a lightweight NMP design tailored to sparse embeddings operators with much lower area and power rather than CGRA. The system optimization for memory-constrained learning models, sparse embedding representation have been commonly employed to augmented deep neural network DNN models with experimental memory to memorize the previous history. The Eisman set explore the idea of the NMBs for a large embedding storage. Although the proposed technique leads to 2 to 3 times improvement of effective NMB reading bandwidth 2.3 GB per sec, it remained far below typical DRAM bandwidth 76.8 GB per sec and cannot fundamentally address the memory bandwidth bottleneck in recommendation models. MNN fast target optimization for memory augmented neural network and the proposed dedicated embedding cache to eliminate the cache contention between the embedding and inference operations. However, these techniques do not directly apply to the personalized recommendation consisting the order of the magnitude large embedding tables. Tensor DIMM proposed a custom DIMM module enhanced with a near memory processing cores for embedding and tensor operation in deep learning. The address mapping schemes in tensor DIMM interleaves consecutive 64 bytes within each embedding vector across the DIMM modules, which performs a high spatial locality of large embedding vectors. It is unusual to apply to this approach to assume the vectors, for example 64 bytes. Given the same memory configuration, our design can perform the tensor DIMM in memory latency, speed up by extracting the additional performance gains from the link level parallelism and memory side caching optimization. The introduction of customizing compressed NMP instruction in RecNMP also fundamentally addresses the CA bandwidth constraint without a restriction on small embedding vectors as imposed by the tensor DIMM. Section 7 is conclusion. We propose RecNMP, a practical and scalable near-memory solution for a personalized recommendation. We performed a systematic characterization of the production-relevant recommendation models for revealed each performance bottleneck. A lightweight, commodity DRAM compliant design, RecNMP maximally exploits link-level parallelism and temporal locality of production embedding traces to achieve up to 9.8 times performance improvement to sparse embedding operation, carried out by the SLR family operators. Offloading the SLS also offers elevated cache content for the non-SLS operators that remain in the CPU, resulting in up to 30% latency reduction for the correlated co-located FS operators. Overall, our system level evaluation demonstration that RecNMP offers up to 4.2 times throughput improvement and 45.8% memory energy saving with representative production level model configuration. Okay. Today I read this paper, RecNMP, accelerating personalized recommendation with near memory processing. Thank you for your time. See you next time.